Hello everyone, I'm Masood Rezai and today we are going to learn the language of money. And no, I don't mean just counting it. I mean understanding how money moves through time. We are diving deep into chapter 1 of J. Robert Buchanan's Introduction to Financial Mathematics titled The Theory of Interest. If you have the PDF open, we are starting right at the beginning, covering section 1.1 and 1.2. Let us start with simple question. Would you rather have $100 today or $100 a year from now? Obviously, you take it today. Why? Because you could invest it, earn interest, and have more than $100 next year. This is the fundamental premise of the entire book. Money has a time dimension. Buchanan introduces a mathematical tool to track this called the accumulation function, denoted as AT. Imagine AT as a multiplier. It told us what's $1 invested at time 0 is worth at time t. By definition, A0 equal 1. You start with what you have. Now, there are two ways this function can grow, and the book makes a very sharp distinction here. First, we have simple interest. This is a linear growth. The formula is AT equal 1 plus I multiply T. Here, I is your interest rate per period. If you graph this, it's a straight line. You only earn interest in your original principal. The interest itself just sits there, lazy, doing nothing. Second, we have compounded interest. This is exponential growth, and the formula is AT plus 1 plus I power t. AT equal that 1 plus I power t. Here your interest earns interest. The graph curves upward, getting steeper and steeper. Now, I want you to look at closely at a specific mathematical Kirk mentioned in the early section of the chapter. It's a trap for the unwary, and ask yourself which is better, uh, simple or compound. You naturally say compound, right? But Buchanan point out is fascinating mathematical facts. If time or t is between 0 and 1, meaning less than 1 period, simple interest is actually greater than compounded interest. Why? Because a straight line connecting two points lies above a convex curve. So if you withdraw your money after just 6 months, technically, a simple interest calculation would pay you slightly more. But the moment t crosses 1, compounded interest takes over and zoom past simple interest forever. In modern finance, we almost exclusively use compound interest because it reflects reality, or we say that money generates more money. All right, let's move to section 1.3. This is where things get tricky, and honestly, this is where banks confuse people. we need to talk about nominal versus effective rates. In the book, you'll see a symbol that looks like this: I upper and is M. This stands for nominal rate compounded m times per year. For example, if a credit card says 18 percentage APR compounded monthly, that's 18 percentage is I upper and is 12. Is the interest actually 18 percentage? No. Buchanan explains that the nominal rate is just a sticker price. To find out what's really happening, we have to look at the periodic rate. If I upper end is M, is the annual nominal is the annual nominal rate, then the rate you actually pay every period is I upper end is M per M. So for that credit card, 18 percentage divided 12 equal that 1.5 percentage per month. Now, if you compound 1.5 percentage 12 times, you don't add up a 18 percentage. You end up with more. The formula in the book related the effective rate or I to the nominal rate. I plus 1 plus I equal 1 plus I apprentice m per m, all of them power to m. This equation is the bridge between the marketing number and the real number. As m, or the frequency of compounding, for the frequency of compounding, we use term m notation. As m increased from annually to monthly to daily, the effective rate I goes up. The text takes to the extreme limit. What happens if we compound every second, every millisecond, every picosecond, every nanosecond? We got continuous compounding. That brings us to the famous number E or Napier number. The formula changed to 1 plus I equal E power delta, where delta is the force of interest. Why does Buchanan spend time on this? Because in financial calculus, which we will see in later chapters, using e power delta multiply t is a much easier for derivatives and integral than using 1 plus I power t. But for now, just remember, always ask if the rate you are seeing is nominal or effective. If you mix them up in a long formula, your answer will be wrong. Now we arrive at section 1.4, the absolute engine room of financial mathematics. We are going to talk about annuities. But before we talk about mortgage and pension, we have to respect that we have to respect the maths that makes them possible. Buchanan explicitly derives the annuity formulas using geometric series. If you remember high school algebra, a geometric series looks like this: 1 plus r power 2 plus r power 3 plus etc. In finance, our r is actually a discount factor. We call it V. It's a Greek letter, and I don't remember how to spell it, but I call it V. V equal I per one plus I, and think of V as a time machine that shrink money. $1 next year is worth V today. $1 in 2 years in worth V power 2 today. So if I promise to pay you $1 every year for n years, the value of that deal right now is V plus V power 2 plus V power 3 uh, plus V power n, or equal V multiply uh, this phrase 1 minus V power n per 1 minus V. The book used the geometric sum formula to collapse this long chain into a single elegant fraction, that a angel n equal 1 minus V power n per I. That this symbol a angel n is the present value of the annuity immediate. Immediate sounds like it means right now, but in financial aspects, it strangely means payment happen at the end of period, like a standard loan payment. And then we have an annuity due, or a omelet angel n. And the relation between them is simple but critical. Since an annuity due gets you the money one period sooner, it's more valuable. A omelet angel n equal a angel n multiply 1 plus I, or equal at 1 minus V power n per d. The text emphasizes that you can derive almost any financial instrument, loans, saving, lottery payouts, just by manipulating this geometric series. If you understand the series, you understand the product. Let's flip the script. Instead of asking what future payments are worth today, let's ask what our saving will be worth in the future. This brings us to the symbol S angel N. This is accumulated value of an annuity. Imagine you are saving for retirement. This is one of the key examples in chapter 1. You put $100 into an account every month. Interest is compounding. The first $100 has years to grow. The last $100 has no time to grow. When you sum all those up, you get the formula S angel n equal 1 plus I power n minus 1 per year per I. Now let's look at the retirement problem described in the book, around I think around sections 1.4.11 or 1.4.12. It poses a classic problem. Phase 1. You work for 30 years and deposit money D every month. Phase 2. You retire and withdraw money W every month for 20 years. How do you equate this? This book sets up an equation of value. You have two choices. Bring everything to present time 0, brings everything to the retirement date time 30. Usually it's easier to focus on the retirement date. The value of your saving at the moment you retire, D multiply S angel 3 years must equal the value of the pension you want to buy, or W multiply A angel 20 years. Uh, and it's notice that. And this balance is beautiful. It shows that if you want a higher withdrawal, you either need to increase your deposit, increase the interest rates, or work longer. Work longer, denoted by increase N. That math doesn't lie. Chapter 1 proves exactly why starting to save early leverages the power of at exponential I plus I power n term in the numerator. We now we are now moving into section 1.5, covering amortization. If you have a car loan or a house mortgage, this section explains why your balance drops so slowly at the beginning. When you make a level payment P on a loan, that money is split into two buckets: interest payment, or IT. This is the money you throw away. It's the rent you pay to the bank for using the money. Principal payment, or PRT. This is the money that actually lowers your debt. Buchanan defines them recursively. The interest due at any moment is the interest rate times the previous balance, denoted by IT equal I multiply uh, B n is T minus 1. The principal part is whatever is left over from your check. PRT equal P minus IT. Here is the tragedy of the amortization schedule. At the start of a loan, your balance B NDC minus 1 is huge, so IT, or interest, is huge. Most of your payment goes to interest, only a tiny fraction chips away at the principal. However, as time goes on, the balance drops, so the interest drops. This leaves more of your payment available to hit the principal. It's a snowfall effect. This book discusses two ways to calculate the outstanding balance at any time t: the retrospective method and the prospective method. The retrospective method is has a look backward. Loan amount accumulated with interest minus accumulated value of payments made. And the prospective method has a look forward. The balance is simply the present value of the remaining payment. Buchanan proves these two are mathematically identical. But usually, the prospective method, looking forward, is faster to calculate. If you want to know what you owe on your house after 5 years, just calculate the PV of the remaining 25 years of payments. We have arrived at the final frontier of Chapter 1, Section 1.6, or yield rates. So far, we assume we know the interest rate I, but in the real world, you often don't. You know the price you pay outflow, and you know the cash you get back inflow. The question is, what is the return on investment? This is called the yield rate, or the internal rate of return or IRR. To find it, we set up the equation to value so that the net present value is zero, NPV is zero, or PV inflows equal PV's outflows. Let's say you invested $100 today and get $100 next year, 20 and the next, and $150 the year after. You end up with an equation that looks like $100 equal $10 multiply V plus $20 multiply V power 2 plus $150 multiply V power 3. And remember, V equal 1 plus I power minus 1. This is a polynomial equation, and as Buchanan pointed out, for any loan longer than 4 years, there is no algebraic formula to solve this. You can just isolate I on the one side. So how do we solve it? The next introduce numerical analysis, specifically the Newton-Raphson method. We treat the net present value as a function. Let's call it fi. We want to find where fi equals 0. The formula for the iteration is I k plus 1 or I new equal I k or I old minus f I k or fi old per f prime I k or f prime I old. This means you guess a rate, calculate the function and its derivative. Yes, we need calculus here. And that tells you where to move your guess. You repeat this loop until you find the exact yield rate. This connects everything. We use the time value of money in section 1.1 and to set up the equation. We use geometric series in section 1.4 to simplify it. And we use calculus to solve for the rate. That is chapter 1 of Buchanan's Financial Mathematics. We went from simple interest to complex algorithm solution for yield years. Thank you for watching, and I'll see you in chapter 2.